Hello everyone, welcome to my video lecture in BK Math YouTube channel. Today I came up with the open proposition and quantifiers. We start our journey with the definition of what open proposition is. Okay, good. We have a definition. An open statement or predicate is a sentence that contains one or more variables. It just contains a variable. Basically, in mathematics, one frequently comes across sentence that involve a variable, one or more variables. In one side that let's say we have P, clearly we just represent with the uppercase letters the open propositions or open statement. We have X is the day before Sunday, Q of X is X plus 4 equals to minus 9. A predicate by itself is neither true nor false with me. That is, in here X plus 4 is equals to minus 9 is not true nor false because X is a variable. If X is 13 plus 4 is 17, which is not minus 9. Again, if X is minus 13, then minus 13 plus 4 equals to minus 9 is minus 9 equals to minus 9. So in this case, the given open proposition becomes a proposition which has a truth value women. That is true. So basically, an open statement is a sentence that contains one or more variable and whose truth value depends on the value assigned for the variables. Like we here, if you assign it X is equals to minus 13 plus 4 is 9 minus. So in this case, the open proposition Q is true. That becomes a proposition with me. So it's clear that each one of this instance involves variables. Let's say in the first one, X is the day before Sunday. Let's say if X, we don't know what X is. If X is Monday is the day before Sunday. It's just false truth value. If X is Saturday that is before Sunday, that becomes true. So when we just pledging inside X, then the given open statement becomes a proposition women. Okay, so but in the other case, it's not a proposition. So as we can't assign a truth value to it women. So however, if individuals are substituted to the variables, then each one of them is a proposition or a statement like we did before women. So proposition an open statement or predicate is a sentence that contains one or more variables whose truth value depends on the value assigned to the variable women like we did before. After we pledging or substitute, it becomes a proposition women, just reduces to the proposition. Now let me remind you, or as a remark, that collection of all allowable values for the variables in an open sentence is called universal set. So it's just a collection of allowable values for the variables in an open sentence. So the so-called universal set, and denoted by the big U. Keeping this in mind, two propositions P of X and Q of X are said to be equivalent if P of A is Q of A for all A in U. That is, if P of A and Q of A have the same truth value, then the two propositions are equivalent with. Now we can develop this with the idea through the example. We have this a universal set U. Now I think this is U is minus 1 minus half 0 1. P of x is x squared minus 1 is equals 0. Q of x is absolute value of x is greater than or equals to 1. Therefore A is an element of the universal set if we try to associate with the definition of the equivalent propositions. So that P of minus 1 we mean we just pledging inside the previous here, the first one, x squared minus 1. If x is minus 1 we mean minus 1 square, then minus 1 equals 0, then minus 1 square minus 1 is minus 1 square is 1, then 1 minus 1 is 0. So that's true. If x is minus half here, then x square minus 1 is 0, then P of minus 1 is minus half square minus 1, then minus half square is half, 1 over 4. 1 over 4 minus 1 is cannot be 0, then this is false. Again, if x is 0, 0 square is 0, 0 minus 1 is minus 1, minus 1 is not equals to 0, that's false. P of 1 square minus 1 is 0, so 0 is equals 0, that's true, mean true, false, false, it has a truth value. Similarly, we have again this form of if Q is minus 1, x is minus 1, minus half, 0, 0, inside this, minus 1 absolute value is 1, 1 greater than or equals to 1 is true, minus half absolute value resulted to half greater than or equals to 1 is false, 0 absolute value is 0, 0 cannot be greater than 1, that is false, 1 is greater than or equals to 1, that is true. This P of A is Q of A for all A in U. This means for all A in U, P of A and Q of A have the same truth value because we have true, false, false, true in both cases. So in this case, P and Q, the propositions P and Q are equivalent, we mean. Okay, equivalent. Again, we have definition. An open proposition P of x is a tautology if P of x is, if P of A is always true for all A in U, that is for all A in the universal set, if P of A is always true, we call this open proposition is a tautology. Let's say x squared is greater than or equals to 0. Actually, U should be a real number in our case, otherwise this cannot be a tautology. If x is a complex number, x squared is greater than or equals to 0, minus 1 cannot be greater than or equals to 0. Let's say if x equals to I, okay, the complex number. That's why without losing the generality, U is assumed to be as a real number. So x squared is greater than or equals to 0 is a tautology, we mean. But I think it's better to discuss about quantifiers. Okay, quantifiers. We have two types of quantifier: the universal quantifier and the existential quantifiers. When we study quantifiers, I think mathematicians really like being lazy if they can get away with it, and one of that the ways that we allow ourselves to be lazy, or perhaps efficient is the better word, to come up with a new terminology and new symbols like the symbols that allow us to collapse the large, more cumbersome things to shorthand. And so when we have large amount of mathematics where we're using the same sort of phrases over and over again, we can just replace it by this one symbol, so it just minimizes. So that's what we are going to do now with this universal quantifiers, like here the universal quantifier, just like an upside down a, and it means for all, for every, for each. Okay, just a little bit, it's shorthand. Now the reason why I care about this is, let's go back to the idea of predicate, because the predicate is something that is sometimes true or sometimes false with me. Okay, but I might have it in the that the predicate is always true, or it could be that for values of x the predicate is true. So this way is why we use quantifier. Using the quantifier, we can change the opening propositions to the proposition. So it just allows you to work with the statement regarding infinite set of objectives. So we have two types of quantifiers, universal and existential quantifier. The order matters in the dealing of the quantifiers. Good. As we observed before, unopened propositions can be converted using a substitution into a proposition. That individuals for the variables after we substitute, then it becomes proposition. But there are other ways that open propositions can be converted into propositions by quantification, either using the universal quantification or existential quantifiers here. So we use the upside down A for the symbol of universal quantifier and means for all, for every, for each, and for existential quantifier, then just want to be represented with the backward E, then refers or it means that there exists for some, or there is, or at least one women. Okay, so it's just pretty easy to study even in quantification. We have to remark that even we will try first, before we deal with the universal quantification, how we are going to represent the statements, English statements, using the quantifier. Okay, I think it's better to exercise the same, write the following statements using quantifier. There is a real number x greater than 0 such that x squared plus 2x plus 3 equals 0. So because there is in the previous, you remember, if there is, then just wanna be represented with the backward E. So there is a real number x, okay, such that this proposition holds. So x squared plus 2x plus 3 equals 0. The other case is the square of any real number is non-negative. Okay, the square of any real number. So every real number, square of every real number is non-negative. We use this universal quantifier for all x, or for every x, for every real number, the square is non-negative. It could be 0 or it could be positive. Similarly, if we have p of x squared plus 1, then x squared plus 1 is greater than equals to 0. So in this case, for all x squared plus 1 greater than equals to 0 is true for any x. Whichever you're pledging inside x squared plus 1, then x squared plus 1 is positive, we mean. Again, in here, p of x less than x squared for all x less than x squared. So in this case, again, this is false because we may have also a counter example. When you're showing for all x the p of x is false, it's just sufficient to find at least one a in the universe such that p of a is false. Such an element is called counter example. Okay, counter example. So for all x, the given proposition is false, women. It is just sufficient to find at least one such that this proposition is false. We call that a is a counter example. Let's say if we have half, half is a real number, therefore half less than, let's say just pledging inside this proposition, half less than half square is 4, half less than 1 over 4 is false, so that means false, we mean. But in here, if there exists some x, for some x less than x squared is true, we mean. Okay, let's say if we have any form of minus 1, let's say if we have x is minus 1 or minus 1 is less than 1 is false. Okay, minus 1 less than 1 is false if for some x, again for some x, if x is minus 1 less than minus 1 square is minus 1 less than 1 is true. That's why this is a true proposition if it becomes the existential quantifier. Similarly, for the proposition absolute value of x is minus 1, the truth value of for some x p of x is false, since there is no real number whose absolute value is minus 1, we mean. Okay, so for some x or for all x, this statement is false, we mean. This statement is false. We need to have a relationship between the universal and existential quantifiers. I think it's better to correlate between the universal and existential quantifier. Negation of for all x p of x is for some x negation of p. Negation of some x p of x mean for all x negation of p of x, we mean. So there is kind of tricky to memorize this type of form, negation of, because we have a plus, then p is plus, negation of a, the backside time and the upside down a, we mean the backward e, again negation of p, negation of p. Okay, so I think it's better to have negation of okay, so if you have negation of this plus p, so negation of the upside down a is here, again this is negation of p, women. Okay, the same true for negation of e. Similarly, we have again negation of let's say if you have the backward e, again p, because this is positive, this is positive, so negation of here mean just the upside down a, and negation of this is negation of p. So we use this variable for all x, and negation of p of x, this proposition holds true. So it's just a bit tricky in memorizing here, which is like negating of the quantifiers. So if you have a universal set U, negation of this existential universal is the universals quantifier, existential quantifier. This and the negation of this mean like we did here, negation of x. Okay, negation of this proposition. This is P like this man. Okay, because this is E, I mean the backward E plus P. So negation of this mean negation of this turned to the universal quantifier. So negation of this mean x less than x squared. So x less than x squared mean its negation is x squared less than or equals to x women, or x greater than equals to x squared women. Similarly, we have negation of the universal quantifier to x plus 1 equals 0. Negation of this mean the existential quantifier. So we make negation for this. So negation of 2x plus 1 mean equals 0, we mean not 0. So that's it. We have also. And we will also look at on the propositions containing quantifiers. We can form a compound proposition like we did last time by joining them with the connectives, okay? And the same way we have formulated last time, compound proposition without quantifier. Let's say U is the set of integers, the universal set. P is a prime number. Q is an even number. R is an odd number. So there exists for an x, or for some x, P of x implies Q of x. If P, then Q will mean. If for some x, a prime number becomes even number, okay? So since there is an x, say 2 for instance, 2 is a prime number, 2 is a prime number, so that's true. Q of x is an even number, 2 is an even number, again true, so true implies true is true women. Again for all x, P of x implies Q of x is false, as you can take the counter example. If x is a prime number, then x is an even number with me. Let's say 5 is a prime number, x P of 5 with me, but R of x, I mean Q of x is an even number. Q of x 5 is not an even number, it's just odd. That's why it's just false. I mean true implies false is true, I mean false. Again for all x, R of x and P of x is false. Again R of x and P of x is false. If for all x, for every x, every odd number and P and the prime number here, let's say this is R is an odd number, let's say 9 is an odd number, and P of x 9 is a prime number, but 9 is not a prime, so that's false. So true and false is false with me, okay? So this is how we compute in combination of compound propositions using quantifier and logical connective. But let's proceed to the quantifiers occurring in combination. Now let's move to the quantifier occurring in combination. Quantifiers can occur in combination. Alright, so far we have only considered cases in which the universal and existential quantifiers occur simply. However, if we consider cases in which universal and existential quantifiers occur in combination, will lead to an essentially new logical structure like we did before. So the following are the simplest way or simplest forms of combinations. For all x and for all y, the relation p of x, y holds here with this representation. Again, there is an x and there is a y for which p of x holds. For every x, there is a y such that p of x, y holds for some x, or there is an x which stands for y in a relation of p of x, y here. So in the first one, for the two universal quantifiers may be interchanged without altering the sense of the sentence. Okay, so it's possible to for all y and for all x in the relation p of x, y holds true women. So universal quantifiers can also be combined with the existential quantifiers for women in here in the slide. Now let's develop with the instance. Letting u is a set of integer, p is the open proposition xy, x plus y is equals to 5. Now let's look at on the choose value of individuals. Choose value of individual. Now for some x, there is an x and there is an y, p of x, y holds. This is always true. Here, this means there is an integer x and there is an integer y. Okay? Say that x plus y is equals to 5. This statement is always true when x equals 4, y is equals to 1, since 4 plus 1 is 5. Therefore, the statement, there is an x and there is a y. This statement holds true, is always true for the universe, for this universe. But the symbolic statement, there are other choices, not 1 and 4 only. Other choices of x and y for which it would be true. Let's say if x 2, y is 3, 2 plus 3 is 5. If x is 0, y is 5, then it's still in the set of integer. So that's true. But the symbolic statement merely talks or say that there is at least one choice. Okay, at least one choice for x and y which would make the statement true. And we have demonstrated on such one choice. But in here, for some x, there is an integer x which stands for all y, and which p of x, y holds with me. There is an x which stands for all y. So this means there is an integer x such that for every x naught plus y, for every x plus y equals 5, this is false. Okay, we have no fixed integer, since no fixed value will make this true for all y in the universe. Let's say if x equals to 1, 1 plus y is 5, then this is 1 plus y is equals to 5 is false for some y. Okay, because if y is 7, 1 plus 7 is 8, could not be 5, so that's why there is an x for every y stands for all y in which this relation holds mean entirely this statement is false statement. So that after it just change it to the proposition actually. And then the C part for all x, for some y, p of x, y. That means for every integer x, there is an integer y such that x plus y is 5. Okay, this is true, holds. For every integer x, there is an integer y such that x plus y is 5. So this is false. This is for all x and some y, there is an integer was either x plus y is 5. This is true. Okay. Let's say if x equals to a, y is 5 minus a. This will always be an integer, so that is true statement. Y minus a is an integer, so it's just a true statement. Again, for all x, for all y, means for every integer x and every integer y, x plus y is 5. This is false. For every integer, it cannot be 5. 2 plus 7 is 9, cannot be 5. So that this will be a false statement. So finally, we conclude that this section with the remark that there are no mechanical rule for translating sentence from English into the logical notations, which has been introduced. In every case, one must first decide on the meaning of English sentence and then attempt to convey the same meaning in terms of predicates, quantifiers, and possibly individual constants will be. So next time I came up with the other video to get similar lectures. You should not forget to subscribe the channel below. Therefore, bye everyone. Nice to meet you. Have a nice day again.